This is my presentation on Lab 1, which is charge tapes. So we are asked to physically create a simulation with charge tapes and compare results to our simulated results on the basis of electric force, gravitational force, and equilibrium. We calculated charge in each tape by Coulomb's law and calculated the number of electrons and charge. And we had the charge from the electrons and the electric charge shown below. So the physics principles that we use for Coulomb's law, gravitational force, and static equilibrium, so we use equilibrium to include the electric and force of gravity to solve for the charge, which is Q1, Q2, which would be Q squared. So our experimental setup includes the charge tapes. So we had a charge tape on both sides. We had one supported by structures and one handled by the user. And then our experimental setup was as given. We had our tape that was 0.2 meters long and 0.0222 kilograms, and our width was 0.2 meters long. So we placed two charge tapes, 0.002 meters long. So we placed two charge tapes next to each other, and then because they're both negative, we would see both positive. That means we would see a repulsion and force. And then we placed the charge tape under the supported tape and measured the repulsion distance. So then we achieved a repulsion distance of 3.2 centimeters, and using the formulas previously acknowledged, we solved for the charge of the tapes and the numbers of electrons lost for that charge. So we used the KQ squared, which is Coulomb's law, to solve the actual charge, and then set that equal to the gravity because our equilibrium principle. Then we divided by that by the number of charge in an electron to find the number of electrons lost. So for the coding setup, we basically use the same principles. We solve for equilibrium, and then we set our constants, and then we use F grav and F electric to find the magnitude of the electric force and the number of electrons lost. So we set it up the same way. Basically, we had E field and force electric to solve the actual force of gravity as well, and solve for the charge and the electrons lost. So coding results had our electrons. There was a slight modification, but that'll be gone into later why that modification occurs. But our actual code had 8.34 times 10 to the 10 electrons, and our code also had 1.35 times 10 to the negative 8 coulombs. I forgot to put coulombs there. So the comparisons of the variations in the results between the actual and computational model can be attributed to multiple reasons. We had assumptions in the actual model, which included assuming that there was no air resistance at the system, also assuming that the system was truly at equilibrium, and then assuming that electric charges and gravity were the only forces acting upon the system in the y direction, and it was truly in the y direction, so we had a cosine and sine component that was kind of lost. And the assumptions in the computational model include each tape had the same amount of charge, and charges were evenly distributed across the tape. So causes for error could include from human error for measuring accurate distance of repulsion distances. We used it with our eye. We didn't use actual measurement tools. So yes, we did use a meter stick, but we used our eyes, and we didn't verify with anything else like a tracker system or something like we did last year. And with handling by user, charges might not be equal and result in non-accurate data. So the massive tape might have not been accurate, and then as well, if the metric was wrong, and then we didn't consider all forces in the y direction. Forces solely in the y direction might have not been not solely in the y direction, which was described earlier. So our what if question was that there would be more minimal changes to the actual results like we saw, like repulsed light, so the tapes would still repel, but there would be a loss of protons instead of electrons. Why is it important to handle the charge tapes as little as possible? What happens when the charge tapes come into contact with your hands or other objects, so it can redistribute the charges around the tape and result in the loss of charge of the tape, and would modify the conditions of the experiment because both the tapes wouldn't have the same charge, and the tapes would be more neutral than negative, resulting in a less noticeable repulsion distance, like a less number than 3.2 like shown earlier. So conclusion, after comparing with the computational and actual model, there are some clear variances in both the calculated models, but the numbers are in the same vicinity in terms of change in electrons lost. But both models aren't entirely correct, as we didn't account for the unequal distribution of charge, loss of charge, and unequal charges between the two tapes because of human handling and error, and applications of other forces in the equilibrium setup, such as air resistance and friction. Thank you for listening.